Okay, so again, welcome all the newcomers and all the faculties present here. I'm Pranav Vak from TY Comp B. I'm going to conduct this session on artificial neural networks. Okay, so looking at the three words, what basically we look at when we are looking at any of the sentence or any of the words is that what meaning they're trying to give us. So in this word that the artificial neural networks, it's made of three words like artificial and neural and networks. So first of the thing, what is artificial, which is which is the man-made thing, like the neural networks. The neural is the word for neurons. It's the plural for neurons. And neurons, as we all know, it's made by nature, right? We don't make it. So whatever we make it, the artificial, the man-made thing which we make it, is the artificial neural, and a network of it, it's called as artificial neural networks. Okay, so let's go to next slide. Okay, so first, trying to look at what is artificial neural networks, let's try to look at what is a neuron. Basically, what is a neuron in the brains. All these neurons are present in the human brain. So yeah, this is a bit biology for you, but I'm sure like it's not very deep. I'll walk you through it. This we only need to focus on three things: the dendrite, the nucleus, and the axon. These three things we need to focus on right now. Okay, so what are dendrites? So dendrites are basically the things which take the input from some other neuron or some other cell or some other etc. Anything. They take the inputs. Their role is to just take the inputs and pass it to the nucleus and obviously the cell body. Okay, so now what's the job of this nucleus? Okay, so this nucleus is actually, like, we call it as the brain of we can call it as a brain of the neuron itself. So whatever the computation is happening, it's happening in this nucleus. Like if we what inference we need to draw from the dendrites, like from the inputs, and what we need to pass as an output, it's all decided in this nucleus. And coming to this axon, this axon acts as an output, like this axon acts as an output, like what you can say, an output for this neuron. This output can be connected to some other neuron, or it can be connected to some like sensory organs, or etc etc. So whatever we see, like we don't see this structure anywhere. What we just see is just the our sensory organs sense something, which is the input. Something gets computed in our brain, and whatever the actions we do is an output. So whatever is happening in between, we don't see that. So that's the part here. So let's now try to understand what scientists tried to did. Okay, so as we all know, the human brain is the most computationally and happens to be one of the most powerful learning tools, or like learning mechanisms on this planet. So what researchers and scientists analyzed, and what they tried to do is, what if we try to mimic this human brain? Like we all know the human brain does simultaneously so many things. We all do simultaneously so many things. And so what if our computer also can do such things? And thus they came up with the idea of artificial neural networks. Like whatever the network is present in our brain, let's try to mimic it. So the neuron which we saw in the previous slide, this neuron, they tried to mimic it by this structure. Okay, so what is this structure? As we all know, we saw the dendrites, which acts as an input layer, and we saw an axon, which acts as an output layer. It's an output unit for our human brain. So here in the artificial neuron, that's the input layer acts as a dendrite, and the output layer which acts as an axon in the actual neuron. And whatever the computation goes on in the nucleus, it happens here in the hidden layer. Now again, why it's named a hidden layer? As I already told you, whatever the things which are getting computed inside our brain, it's not visible to us. So like it's hidden. So they gave the name, it's hidden layers. Okay, so this is a simple single artificial neuron, and the input layer. What is the role of the input layer? Okay, obviously take the inputs from the data set, or take the inputs from other neurons in a network and pass it to the further layers. That is the hidden layer. Now, what is the role of the hidden layer? The hidden layer is apply a certain function, apply something to it. We'll see what it exactly applies to it. Apply something to it, then again apply something to it, like 2-3 times it applies to something. and passes that output to the next layer. Each layers the task of each layer is to just compute its own thing and give the output to the next layer. Okay, so as we go through it, we reach the output layer. So this output layer finally wraps up all the things, whatever the computation is done, it wraps up all things and just gives an output value. Okay, so output value can be continuous, like it's a price. Suppose the housing price example, it can be like 2 lakh rupees, 5 lakh rupees. It can be a continuous value. It can be a binary value, like yes, no, 1 0. Is it a cat? Is it a dog? 1 0, or a categorical data, something like that. So this is what a neuron looks like. Now hold your picture, hold your like vision to a single neuron, and I will show you what a network of neuron looks like. Whoa! So this is the network of all these neurons. You might be wondering like, oh, it's difficult. Just leave it. We'll not be able to study it. But just trust me, it's not that very difficult. I'll walk you through it. I'll walk you through the structure. Now let's just consider this as a single neuron, like this the first thing. Suppose these are the two input layers. This is the hidden layer, and this is the output given by that hidden layer. And this output is now given to a next neuron, the next input of the next neuron. So maybe this may be a neural network, again a single neuron, maybe, or something like that, which doesn't have a hidden layer or something. And again, this output is again passed on to the next neuron or something like that. And thus, this is a network of all small neurons. And let me tell you one thing: the input layer is obviously going to be one, output layer is obviously going to be one. The layer, I'm trying to say, the layer will be one. It can have multiple circles, like it can have multiple units in it because of the categorical data or something like that. It can have multiple units in it, but the layer is one. But what is not single is this hidden layers, like whatever is which is not an input layer and which is not an output layer is all categorized into the hidden layers. And yes, there can be multiple hidden layers. So let's just walk further now. Okay, why do we require ANN? We already have learned logistic regression, linear regression, and all these things. Now, why do we require the artificial neural networks? And the answer is for the nonlinear classification example. Now consider this the nonlinear classification example, and you plot the graph of your features x2 and x1, and you get a graph of something like this. Okay, so now if you, as a data scientist or data analyst, you try to first implement suppose consider logistic regression model. It will give you a decision boundary, something like this. Okay, it will roughly give you something like this decision boundary. Fair enough. It satisfies our aim. Okay, but at the same time, what it will give you is this function. Is this the g is the sigmoid function? I'll come to that point later. What is a sigmoid function? Okay, so just consider this is it's a simple function. What the function of all our parameters and all our features. So this is the x1, x2, fine. It's just a single like degree 1 term. Let's consider this term. Okay, degree 2, we are still fine. Degree 3, okay, we are quite moving to some higher order terms, but still. But now, if you try to see this and the further terms, it is x1 cube x2. That's the 4th degree term. Okay, and now if you still try to imagine, these are only the two features, x1 and x2. But in the real world problem, we will not have two features for any problem. We'll have like 100 features, some 1,000 features we would have. And well, in that case, if we consider just the second order features like x1, x2, or x2, x2 square, x1 square, etc., all these second order features, and for the 100 features, we would add up to 5,000 features. And yes, as we all know, it would be computationally much more expensive. And the first and foremost thing anyone tries to see in your model is the cost. May it be like computationally expensive, or it is a bit time consuming also. So, and memory also you will require that much more. So yeah, in terms of money, you will require a huge amount of money to implement that model. So what is the like answer to this? And yes, there the answer lies artificial neural networks. And this is the main role of artificial neural networks, that when you are having large number of features and you cannot your model goes to, for computationally expensive, you use artificial neural networks. Okay, so I'm talking about neural network, neural artificial neurons, etc., etc. Now, how let's see how exactly does this work. Okay, so we already have seen some here, like artificial the input values we have, the x1, x2, x till xm. Suppose the m values, whatever the input we have given from the data analyst, we are going to take as it is in the first layer. Okay, and we are going to take we are going to wrap up things up and give the output in the terminal or whatever the screen we are using. Okay, so now let's check what is happening in this middle part. Okay, so what exactly is W1, W2 till Wm? Okay, so these W1, W2 till Wm are called as weights or parameters. These weights or parameters are the thing that how neural networks learn. Like whatever we have seen, like input value, it's fixed. We cannot change the input from the data set. And output value. Output value is also like it's dependent on our whatever the computation we make, but it's the standard. Like we have for the training set, we have already have the output of our data set, so it's also fixed. Whatever is not fixed, which whatever is variable, is here. It lies here. So okay, so these parameters and these W1, W2, W3 are the main roles, are the main variables who change their values and adjust our or tune in our artificial neural network, and thus we get a strong output. Okay, so what are the steps? Step one in this middle part. What is the step one? Step one, just multiply these weights by these input values, like x1 into w1, x2 into w2. We all like just multiply all these things and take a summation of it. So this is our first step. Whatever you're looking at here, the summation of wi and xi. This is our first step. Now, what is our second step? Apply an activation function to it. So this function is an activation function. We need to apply to it. Okay, so activation function is like, you can consider it as some function which we need to apply it and apply it so that we will compute something from it. This is the second step. And the third step is, yes, pass on the value to the next layer. We got the output from this layer and just pass on it to the output layer. So as you all can see, the direction of the flow is from left to right. Like we were in the input layer, we went down to this hidden layer, and then we went ahead to the output layer. So it's left to right approach. So this has a name. So this left to right approach is also known as forward propagation. So yes, let's see further. Okay, so now I talked about the sigmoid function, the activation function, which actually I talked about. There are basically we mostly use two activation functions. There are many, but we use two activation functions. One is the sigmoid function and one is the rectifier function. So let's see what is a sigmoid function, sigmoid activation function. So here you can see the sigmoid activation function is it's a graph plotted again, y versus this summation wi xi. So we have our like in this 0, and if we have a negative value for the summation, we'll get something like value here in from starting from here till it goes down to 0. So this, as you all can see, why it is the most widely used activation function, as it has a smooth curve. Now, what is the use of this smooth curve? Okay, so whenever we try to deal with some probabilities in our output function, what we require is a like 86% probability or 96% probability or like let's say 75% probability. So this 75 number or 86 number, you will not get this number in a like straight or whichever curve is smooth. You will not get this number in that. So this number you will get in the smooth curve. Okay, so suppose the value of suppose the value is something like something like between here. So you will get a corresponding y value here, which may be 0.8 or something like that. So Yes, so this is the most widely used activation function in the output layer, and because of the probability in whatever problems we are trying to predict the probability, we use this function. Okay, so now what's the mathematical representation of this function? It's 1 upon 1 plus e raised to minus x. Now this x is nothing but the summation we got here. Whatever the summation we get here, we pass it as an as an argument to this function, the x, and it gets computed 1 upon 1 plus e raised to minus x. This is the simple graph of that function. Many of you might have studied in mathematics. Okay, so this is the all about sigmoid function. Now let's see what is a rectifier function. Okay, so rectifier function, as you all can see, as I already told you that because of the smooth curve, the sigmoid function is mostly used in output layers. But what here? Like it doesn't have any smooth curve, but still it is used in many of the hidden layers. Okay, so it mostly deals with the hidden layers. So this rectifier function gives you a straight output of 0 if your value is negative, and it suddenly increases, like it's gradually increasing from 0 onwards to the value. So this is the mathematical expression for it, that the max of x or 0. Like if we have a negative value, we straight away get a 0, and if we have some positive values, we get a corresponding value for it. This is again one of the most popular functions used in artificial neural networks. It's 0 at start and then suddenly gradually increasing. And yes, the code name for it is ReLU, ReLU. Yes, we need to input this name when we are going to use this rectifier function. And this range is like from 0 till maximum value will get is a 1. Also, I forgot to mention the range of the sigmoid function. Okay, the maximum value you will get is 1 and the minimum value you will get is 0. So this function always output the values from 0 to 1. So again, yes, it's easy to get us the probability from it. Like just multiplied by 100, you'll get the probability. Okay, so now let's jump into some real world problem on how do neural networks work. Let's take an example of predicting the housing prices. Like you have a house in a certain area. So what are the features? So some of the features might be the area, whatever the area the house is present in, what number of bedrooms present in the house, maybe 3, 4 bedrooms or 0 bedroom for that matter. Then distance from the city. Okay, it's located like 10 kilometers from the city. So how that feature might affect the cost of the house, and the age. So this may be some of the features. Yes, there are more, but let's consider these 4 features at the first. And whatever our aim what our aim is to predict the price of the house. Okay, so first is the input layer. Input layer gets the input of all, like whatever the data set we provided, it gets the input from it. And so let's take into consideration, like the first unit is considering is taking the input of the area. Second is dealing with bedrooms. Third is with distance to city, and fourth is with age. Okay, so now these units pass on their values to the neurons or the units in the hidden layer. So okay, so what happens in this hidden layer? Okay, so as you all can see, I've just this neuron, we are looking at this first unit. It only has 2 arrows, which is this and this. Okay, so why only it considers the 2 features, like area and distance? It might not, it's focusing on just area and distance from the city. As distance from the city will decrease, and area increase, the price of the house will gradually increase. But it specifically focuses on these attributes, as it doesn't really want the number of bedrooms or age something. It's just trying to figure out what is the relationship between area and distance from the city. This is the role of this unit here. Okay, let's come to this unit. This unit is taking the input from 3 units. This is the area, bedrooms, and age. Okay, so obviously you can all figure it out. If area of the house increases, price of the house increases, number of bedrooms increase, the price increase. And age is a very very fascinating factor here, because if the age of the apartment is like from 10 to 20 years or something like that, its value gradually decreases, right? So if it's too old, if it's old, we don't actually really pay for it. At the same time, if the age is like greater than 100 or something years, it's a historical monument at a sudden, and so it will have a huge value. And so this neuron is just trying to figure it out, what is the age of it. Like, it's a very fascinating feature. So might be if it's 100 or 200 years back, it's places of 200 years or 300 years of age, distance from the city, bedrooms or area doesn't really matter much, because it's a historical monument. So each of these units is trying to figure it out, what exactly parameters are affecting it, and they're trying to do it individually. So here, what we saw at the back was x1, x2 feature, or x1 cube, x3 feature. Whatever the features we saw there, these all small units are trying to figure it out, what these features actually, these x1 square or x1 square, x2 square, something like that. These are trying to understand what these features are. Okay, so we have answered this question, what each unit in the hidden layer is trying to compute. It's basically trying to check what features are affecting the price, and it passes on the output to the next layer. Okay, so now how do neural networks learn? Like, as I mentioned you all, it takes on the features and it just computes everything and it just passes on to the next layer. Okay, so the amazing and most fascinating thing about artificial neural network is you need not pass any argument or any feature on your own. It will learn it will learn on its own. Like, suppose we take an example of a cat and dog. Suppose we want to go through like logistic regression or something other model. What we need to hard code it, like, okay, if the ears are like straight, it might be a cat. If the ears are fallen, it might be a dog. Or if it, etc., etc. Like, if the size of that animal is something bigger, it might be a dog. If the size is relatively smaller, it might be a cat. Like, all we need if we are doing hard coding, we need to pass all these things in the in whatever the algorithm we are using. But in the neural networks, what we do is just we give them 1,000 pictures of a dog, 1,000 pictures of a cat, and we ask the neural network, like, okay, go neural network and just learn for me what is a cat and what is a dog. And it will learn its own based on the whatever the input, how many inputs you have given and what input you have given. It will try to figure out something from all the features and try to relate it, and it will learn what is a cat and what is a dog for you. So you need not learn anything for like you need not pass any arguments to it. Okay, so what exactly neural networks learns on its own based on the inputs we have provided them. Now, how exactly it does it? So we have seen the thing, like the forward propagation. The input value, we get the input from the data set. We pass on this input to the hidden layer, or something happens here. Whatever the computation is happening, it happens here. It passes our value to the output layer. Output layer wraps it up, and we get a value y cap. Let's consider this as the output which is given by our neuron. Let's consider first the single neuron. We'll go to the network on the later stage. Okay, so this is y cap is the output value we got from a neuron, and y is the actual value we actually have in our training set. Okay, suppose whatever the output value, suppose we outputted the housing price as, suppose, 2 lakh rupees, but the actual value is 5 lakh rupees. So yes, there is an error in our neural network, right? So we need to try to compute that error, so that the error thing is measured by this function, which is named as a cost function. It is the measure of the error in our output, or how far is our output from the actual expected output. So what we do is we need to minimize this error, right? If we try to minimize that error, we are trying to correctly predict the price. If it's 2 lakh, price, actual price, and we are almost predicting 1.7 or 1.9 lakhs, the error is much reduced, right? So we need to reduce, we need to minimize this cost function. So how we do that? We simply plot y cap, y and cost function at the same time. Now we check. Now we this function, the cost function, is applied, that the half of y cap minus y whole square, and likewise we get something value, like suppose let's take that value as x. Suppose we got a value x. That cost function is our, suppose, x. Okay, fine. Now what we do? We got an error. We try to figure it out what an error is, and we got some error. Okay, so now let's jump forward before coming to that error part. Okay, so now we need to minimize it, right? We need to minimize this cost function. So what we do here is we plot the cost function c versus the value, that the y cap, whatever the predicted by our neuron, and we get something, the curve. Suppose like this, we get a curve. It's a two-dimensional curve. Just imagine, and we'll get something curve like this. Okay, so now what we need to go to is that the minima, right? So our ultimate aim is to reach the minima. This is the minima of the curve. Our ultimate aim is to reach this minima. And okay, so one of the approaches, the brute force approach, like plot all these points on the graph, like take your neural network from all the possible values of the cost function, and then choose a minimum value from it. A brute force approach. Like if you have an array, you have given, suppose, 100, 80, 90, sorry, 100, 90, 80, 60, 70, and right from 10, and again 10, 20, 30, 40, 50, 60, 80, 90. And so 10 is the minimum value. You select that 10 as the minimum value for your cost function. This is one way, but it will again take you to computationally expensive way. And so an algorithm or a technique to not go by that way is gradient descent. Gradient descent. Okay, as the name says, again, gradient is the slope, and descent is we need to go down, like descent. We need to descend something. So what exactly we need to descend? We need to descend this curve, like this curve. Okay, so we are here. Suppose we start at this position. This is the first position of R, and what we do is we calculate the slope of it. Okay, so we get a slope here, and we notice that this slope is negative. Oh, fine, the slope is negative, and we need to descend also, right? So we are on the same track. Like if the slope is negative, so we are going in this direction, and yes, we need to go in this direction. So we don't. What we do is we just move on to this direction. At the second step, we reach this stage, this step. Okay, now again, what we do? We again calculate the slope of it, and now we notice that, oh, our slope is positive. Okay, so our slope is positive, so we are moving in this direction. But is this the direction of our minima? The answer is no. Our minima is already like left behind. If we are traveling from Pune to Lonavala, we already have reached Mumbai, so we need to go back to Lonavala. So we need to reverse our direction. Okay, so we reverse our direction, and we again go back to, like, again go backwards. We reach here, suppose. Again we calculate the slope of it. Again we get a negative slope. It tells us, like, yes, we are going in the right direction. We need to descend down the hill. And okay, so now what's the difference between this step and this step? Both the steps are giving us the negative slope, but what's the difference in it? As you all correctly might have guessed, the slope is much more here, and the slope is much less here. Okay, so what does this need to do with us? Why do we need to we need to worry about how much is the slope? Okay, so as you all know, how much factor, or by how much parameter we need to go back, or we need to move forward, is decided by this slope. Like if we are traveling from, like, Pune to Lonavala, if we let's just consider this as a hypothetical situation. You need to, suppose, press on your accelerator twice, suppose. So like if you are still at Pune and you need to go to Lonavala, what you will do? You will press the accelerator 5 times. But if you have just like from 5 or 6 kilometers from Lonavala, at that time you just need to press the accelerator 1 times. Like you will reach Lonavala. So that's the thing done by this slope here. The slope gives us the value of the learning rate. We call it as a learning rate. That's alpha. It's denoted by alpha. So this learning rate is decided by this slope. And if this slope is very steep, the learning rate is high. And if the steep is very the slope is very low, it means that we have almost close to our destination, and so this learning rate is very small. And so yes, we apply the learning rate, we again go down the hill, and now we have reached this stage. Okay, so now this is a zero slope state. That is the slope. And so as the slope is zero, yes, we have now finally reached our destination, and this is our minimum value. So here, as you all can see, we just need to take 1, 2, 3, and 4 at the max, something like that. The 4 steps. In 4 steps, we got our minimum value. But what if we gone through our like previous brute force method? We need to visit each and every point once, and then need to decide which one is the minimum. So obviously, this is the best thing. Like we just need to do 4 computations, and yes, we have reached our minimum value. Okay, so how many times you need to repeat this step? Like if you're in this stage, you need to go to this stage, you need to go to this stage, and you need to go to this stage. So how many times you need to repeat this? Okay, so until we get our minima, until we get our slope as 0, we need to do all these steps. Okay, so this is a simple 2D curve, and let's take a view to a 3D curve. Whoa, it looks something like some Sahyadri mountain ranges, and okay, it's a Sunday, I know. Let's try to understand what the gradient descent in 3 dimensions. It's just I'll walk you through it. If you are on the top of the hill, you just look. If you are on the top of the hill, you just look all around. Where is the valley? And you go towards the valley. This is the basic concept behind it. Many of you might have done trekking or so. So when you are on the top of the mountain and you need to descend down, what you all do, the same thing computer does here. So we take this step. Okay, we find that we have something missed. We have something gone wrong. Okay, so we go to this step, and again we go to such steps, and we reach the valley. So this is the gradient descent in 3 dimensions. Okay, now let's come to the point. Now we have minimized our cost function. Something like we got our y cap value, we got our y, we had our y, we computed cost, we computed the error function, like the error function, and we minimized it. Now okay, so now what next? We still have that error, right? We have just have minimized that error, but we still have that error. So what we do is we go back again in the in our neuron. So this cost function is the cost function is again passed on. These values are again passed on back to our neuron, and we go back and we update this W1, W2, and WM. Okay, so input values we cannot change, but the parameters, that are weights, we can change, and that's how a neural network learns. Change by adjusting the weights. By adjusting the weights, it learns. Okay, so now we came back, we adjusted the W1, W2, WM. Now we take the new weights, the new W1, W2, WM. We again multiply it by this, and we again go in this direction. Again we get some y cap value, some actual value we already have. Again we calculate the cost function. Again we go back here and do all these steps. Okay, so now in the previous slide, you might have noticed the direction of the flow was from left to right. Now the direction of flow is from right to left, because we are going back in our neuron, right? So that's the name, the back propagation. We are propagating backwards in our neuron and adjusting our weights. So the name, back propagation. And the most important thing we all need to remember here is adjust all the weights simultaneously. Okay, what does this exactly mean? Now let's consider we have a single row. Then we pass on to this input values, and we just go in the output value, we get the cost function and backpropagate the error in our neural network and update the weights. Okay, for first row we have updated that, so our weights are something different. For the first row, first cell, RW1 is updated individually, and W1, W2 it's been updated individually. So so it's not a good thing, right? If we update the weight, like if we update W1 and we don't care about W2, WM, the that all the parameters, like it would be affected, right? So the first and foremost thing we need to remember is adjust all the weights simultaneously. We are looking at if we are back propagating the error in our neural network, we need to adjust all the weights at the same time. And this so when we back propagate to all the weights are updated, and these apply to the every row, each and every row in our data set. Okay, so let's move forward. This concept is basically known as back propagation. Okay, so now let's try to imagine what actual thing is happening here. Consider this as your data set. You got a data set from somewhere. This is the data set, and okay, so this is our output. This is our output column, and these are our input columns. Row ID doesn't matter as much, so we are not going to take that row ID. Okay, so this row, the 12, 6, and 78%, this is passed on to suppose this neural network, this neuron. So we can see 1, 2, and 3, the three input units. Each the study is passed on to this. The sleep hours is passed on to the second, and the quiz percentage is passed on to the third. Similarly, this all are there's the eight whatever the neurons you are seeing here. It's actually the same neuron. I've just like multiplied it so we can understand it, like what exactly happens here. So now suppose consider the first row is going to the first neuron, second row is going to this second neuron. Likewise, the third row to the third neuron, fourth row to third neuron. Actually, it's going simultaneously. Just consider it as a separate, so that it would be easy for us to understand. Okay, so simultaneously all the rows are passed on to the neuron. It calculates the y cap for the first row, the y cap for the second row, third row, fourth row, etc., etc., until the last row. Also, we have our output value already present, 93%, suppose. So this is the actual output for the first row, actual output for the second row, and so on. So now we got so now we got like our y cap and y. The next thing to do is calculate the error, whatever the error we are facing here. So this cost function is the summation. Now we take the summation of all this, summation of all this, the output values we got, the minus the actual output, the whole square, the half of it. We take the summation of all of this, and we calculate a single cost function, a single a single thing for all these things. And yes, this thing is the error we got. We do some gradient descent on it, like we check how far are we from our target, and we backpropagate the error. We backpropagate the error through our neural network, and then we adjust W1, W2, W3. So these W1, W2, and W3 are adjusted at the same time for all rows. So this W1 is equal to this W1, which is equals to this W1, which is equals to basically all W1s present here. So at the same time, we apply it to the all rows. And that's how this data is again fed into the neural networks, and the weights are adjusted. Now again, the weights are adjusted. Again, we calculate the y cap, and again we go to the cost function, minimize the cost function, and again go back, adjust our weights. We repeat all these steps again and again until we get a minimized cost function. And if we get a minimized cost function, yes, that's our ultimate aim. So we have reached our target. So now let's just try to combine all the things what we have seen. And if you are given actual neural network, what are the steps involved? You need to what are the steps involved you need to do? So the first and foremost step is randomly initialize the weights to small numbers, close to 0 but not 0. Okay, so why this thing? We need to randomly initialize our weights, like W1. The weights are W1, W2, WM, whatever we talked about in a few minutes ago. So we need to randomly initialize it, but not to 0. If all the weights are 0, our summation, like we saw in the first step, let me just take you back. Okay, the first step is here. The summation will be 0 because we are multiplying the weights with x, As the summation is 0 and we are applying an activation function, let's suppose, imagine it's a rectifier activation function, we'll again get a 0. A 0 will be passed on to this, and everything is 0. So we don't really want that. So we randomly initialize the weights to close to 0, but not 0. The step 2 is the input the first observation of your data set in the input layer, each feature in one input node. So whatever we saw here is it's that thing again. Then the next step is the forward propagation. The forward propagation, we move from left to right. The neurons are activated in a way that they impact each of the neurons activation, and it's limited by the weights. The weights are the controlling parameters here, and propagate the activations until we get a predicted result y. That's the y cap basically. Then what we do, we compare the predicted result and get the actual result, compare predicted result to the actual result, and measure the generated error. Okay, now we have calculated the error. Now the next step is the backpropagation. We need to backpropagate the error from right to left and update the weights accordingly by how much they are responsible for the error. And yes, as I mentioned you all, the learning rate or the alpha, alpha, and the alpha here decides by how much we should update our weights. Now the step 6, repeat steps 1 to 5 and update the weights after each observation. That's basically called reinforcement learning, the name for it. Or repeat steps 1 to 5, but update the weights only after a batch of observations, batch learning. You need not worry about much. But what exactly is batch learning? Like we all saw that we pass on one row to the neuron, we try to figure out what is the error, and we backpropagate the error and we update the weights. This is we just do for one row, right? So if we do for one row, it's reinforcement learning. If we do it for a batch of rows, it's batch learning. Like we update the weights for a batch of say 30 rows or 5 rows or 10 rows. Then it's like for all the 10 rows at a time, we are updating the weights. You're not updating it for each row at a time. And then the final step, the step 7, when the whole training set is passed through the ANN, that makes an epoch. Redo more epochs. So whatever the steps we have done so far, we need to repeat all these steps for a certain number of epochs, so that for the sure, like we didn't miss out anything, like some of the parameters or something like that. Okay, so that's all about theory part. Now let's jump on to the actual example of an artificial neural network. So let's try to understand what is the problem statement given to us. Okay, so a data set of bank is given to us. Okay, before moving to that, I guess I have not shared you the drive link. First, I'll share you the drive link for it. Okay, so whoever wants to do it like simultaneously with me can just open the drive link for me, and anyone could just unmute and tell me if the link is fine and everything is opening correctly and all.
Yes, Pranav, it's working.
Okay, so when you will open that folder, you will get something like this. Okay, so this is our data set and this is our notebook. Okay, so let's just try to understand what is our data set first. Okay, so this is our data set. Let's again visit our problem statement first before viewing what is our data set. Okay, so our problem is you are given a data set of a bank. Okay, it has all the information of its customers. What is the credit score? What is the gender of the customer? What is the bank balance of the customer, etc., etc. And what the peculiar function, what like something a bank observed was, like if the bank customers are leaving the bank, some of the customers of the bank are leaving the bank is not able to figure it out, like why they are leaving, and in the future who all customers would leave the bank. So as a data analyst or data scientist, they hired you and they asked you to like just relate all these features. They are giving you the data set for like the bank has observed the customers, bank observed its customers for 6 months, and based on it, they checked how many of them left the bank. So they have given you data set for the customers for a span of 6 months, and they have asked you to generate some relation, or they've asked you to generate some model which will tell them which customers after 6 months would leave them. And obviously the business is important to everyone, so the bank needs to know that whether they have to focus on XYZ customer or ABC customer, because if the ABC customer is leaving anyway, he will leave, and if the XYZ customer is like doubtful if he'll leave or not leave, then bank could focus on it. So this is our problem statement. So now let's see what is our data set. Okay, so our data set, here is the first column, row number. Basically, this is the row number, what the row is as. The customer ID and surname of the customer, credit score, geography, gender, age, tenure, balance, number of products, etc., etc., and exited. Exited is like, has the customer left the bank? It's a training set, right? So if they have already collected this data for 6 months and they've directly given us. So if exited, yes, like if the customer has left the bank, it's 1. If the customer has not left the bank, it's 0. Let's try to see how many columns we have. Okay, so there are 1,000 columns. Sorry, no, I'm not sorry. It's my mistake. There are 1,000 rows in this data set. So this is the actual data set, but 1,000 is again a small number for any bank. A bank has like lakhs and lakhs of customers, so it's just like the interpretation of a real world situation. But 1,000 is not a small number as well for our data set. Okay, so what at the first sight what we notice is the row number, the customer ID, and the surname has nothing to do with has the customer, as he or she exited the bank, right? The row number is not deciding something, it's just a row number, so it's not deciding whether the customer left the bank or not. Same with the customer ID and same with the surname, it's just the bank records, and so they have kept the customer ID and all the things. But yes, whatever we are viewing here is definitely going to matter our neural network, because what was the credit score of that customer before he left the bank? In what geographical region was the customer before he left the bank? What's the gender, age, tenure, balance? What was the bank balance? It's the most important thing. Is that if the balance is 0, the chances of it is leaving the bank is more, right? Okay, so the number of products it has, the number of products is basically something, the bank parameter, like it has something like how many bank product does the customer has a card, has credit card, CR card. So is the customer having a credit card or something? Is he an active member? Okay, so what is an active member? So there's rules for each and every bank to determine what is an active member for each bank. Maybe it is like, if you have done some transaction in 6 months, you are an active customer, if you're an active member. If you have not done any transaction for, let's say, 3 to 4 months, or if you have not done any cash transactions in 3 to 4 months, you're not an active member. It depends on bank to bank. So our bank has given us the data. Was the customer an active member or not? The estimated salary, bank somehow did some jugaad kind of thing, and they got the estimated salary of the customer, and they have given this attribute and exited. Their exited is our output value. Okay, so let's just jump again to our drive, and let's just, I'll first download. I've already downloaded it. You all need to download this data set. So please, I request you all to download, whoever are doing hands-on with me. Okay, the next thing we'll open is our Jupyter Notebook. We'll open through Google Collaboratory. Okay, it's just loading, it's taking time. Yeah, it's got loaded. Okay, so this is the rough structure. This is you all might have opened with me. So this is the rough structure. We are dealing with artificial neural network. So what are the steps in it? First and the foremost thing, we need to import the libraries. The second part is like the first part is data pre-processing part, which is the most important part in any of the machine learning model, as it comprises like you can say 60 to 70% of your whatever the efforts you put in, you have to put it in data pre-processing. Then actual part 2 is actual building of the neural network. Part 3 is the training of it, and part 4, obviously, after training we need to make the predictions and evaluate our model, like how well our model perform. Okay, so let's start. I'll just make a new code cell here, importing libraries. So first and foremost part, our favorite, the NumPy library, our favorite library. The library we need to like import, then import pandas as PD. Okay, the second most important and the third most important library we need here is the TensorFlow. So it was a prerequisite for it. And if you are in Google Collaboratory, you need not worry about is the TensorFlow like installed or not, because Google will directly give you that. If you are using your Jupyter notebook, you need to first install it. Okay, so TensorFlow as TF. Okay, so before running it, let's just upload our data set here. Okay, so you need to go here in the files. Okay, it's taking time to connecting us to a runtime and enable file browsing. Okay, it's taking time. Let's just wait. It will connect. Initializing. Connected. Good to go. So here you will see three options: upload to session storage, refresh, and mount to drive. I'm selecting this upload to session storage. I will just just go to the folder, the data set where I've downloaded it. Okay, so here is our data set, and let's just open it. Let's just click OK, and yes, it's uploading. It will again take some time. Yeah, it's uploaded, and here we can see the churn modeling.csv. Yes, the dataset have been uploaded, and we are ready to deep dive into the code part. Okay, so we have typed all these things, the importing all the libraries. Let's just run that code cell and check if there is error. No, it ran well. Okay, so we have imported the libraries, what all libraries we need. Now let's just jump into the part 1. That's the data pre-processing part. Okay, so first thing is importing the data set. Again, I'll add a code cell here. Code cell importing the data set. Let's just name it as a data set, the variable, and pd dot read csv, as we need to like read our data set and mention the name churn modeling .csv. Okay, the M is capital. Okay, so this will read our CSV and store the values in our dataset variable. Okay, now just let's just put all these values in the x and y, our standard NumPy arrays. So x is equals to dataset.iloc, iloc. Then something we need to mention here, dot values. Okay, same thing with the y, dataset.iloc dot values. Okay, so now what thing we need to like just input here? We need to input what all columns we require. Okay, so first thing, all the rows we require, so a colon, comma. Now how many? We require all the rows, so a colon and a comma, and what all columns we require. Now let's just go back to our data set and let's just see how many columns or what columns exactly we require. Okay, so as we all discussed, row number, customer ID, and surname. That these three columns.
Pranav, sorry to
Uh,
interrupt.
yes, ma'am.
Yeah, Pranav, there may be students who are using Collab first time. Okay, so can you please go little slow? Go slow.
Okay, ma'am. Okay, fine.
Yeah.
I'll
So
I'll
might
go
be
slow.
people are just opening Collab for the first time. So just go slow for the initial few minutes. Okay.
Okay. Okay. Okay, ma'am.
Yeah.
Okay. 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 So first, again, I'll walk you through it. First, we went to the drive link which I shared you just now. The drive link will contain the data set required for us and the neural network, like the notebook, the basic structure of the notebook. Then we saw the data set. We opened the, like, how to open this. Okay, let's just see. Double click on it. You'll get an option here. Open with Google Collaboratory. Just click on that. The file will be opened in Google Collaboratory. Okay, in the Google Collaboratory, you will be visible to, like, these all things will be visible to you, not the code cell. Okay, so this is the basic structure. In the importing libraries part, after that part, we need to just add a code cell. So here is the code cell symbol, and just click on it. A new code cell will be added to, your notebook. If you like, if we need to, like, just rearrange all these things, here is an arrow, like up arrow, down arrow, something like that. You can just do if you have mistakenly pasted the code cell somewhere else, you can use these arrows to move it down, forward. There is a delete option to delete the code cell or whatever the cell is present here. If you have went wrong somewhere, you just can delete and start fresh. And the first and the foremost thing, upload the data set. So first you need to go to this icon here, files, and after going to that files icon, it will be like connecting. It's just connecting, initializing. It will take some time to connect and initialize. And after that, connecting and initializing, you will be able to see three icons again here, which is upload to session storage, refresh, and mount to drive. So I had already downloaded the dataset, but you need to download your dataset on your machine through this drive link. And when you will go here, just say upload to session storage, and choose where your like dataset you have downloaded. Choose that file and click open. It will again take some time to run. Here you will see at the bottom, like, where like it's getting uploaded. And once it's connected, you will see the name of the dataset here. If you're able to see the name of the dataset, the churn modeling here, that means yes, you have correctly uploaded the dataset. Okay, is this visible? I'll just zoom it a bit little. Anyone could please unmute and just tell, is all the things visible here, or I'll just.
Yes, Pranav, it's visible.
Okay. So after that, just like import numpy as np. Just type these statements, and you'd be importing the libraries in in this session. After that, just click here, the play button, something like that. You see this icon here, the run cell button, and if you click here, it will run. It will take some time, and when it's finished, hope it doesn't give you any error. If it gives any error, check the spellings and all. Okay, so the next part is data pre-processing, importing the data set. In the data pre-processing phase, the first part is importing the data set. So PD, that pandas library, PD, we short named it PD. So PD.read CSV. So whatever the data set we have, it's in CSV format, comma separated values. So CSV format. So you need to just pass that name, pass the name of the our data set here, the churn modeling. Be sure that C and M are capital in the naming, or if you have changed the name while downloading, it's the name, basically. Whatever the name you have mentioned while downloading, it's the name, churn modeling.csv. Okay, so dataset dot like dataset is equals to read CSV, and we have just read the CSV file. Now the next thing is we have just loaded our dataset, right? We need to take all that columns in an NumPy array. So this is the step. Let's take two arrays, X and Y, standardized arrays, standardized like nomenclature. The dataset dot iLocation, something values you need to mention here. Okay, I made a mistake. Okay, some values you need to mention here, dot values. Now we'll see what exactly you need to mention here. Okay, so as these are the square brackets, you need to mention the row and the column, like what all rows you need to include and what all columns you need to include here. So the colon first, the first colon stands here like we want all the rows. So here is our data set. So we want all the columns, right? All the 1,000 columns. Sorry, I'm again mistaking. All the rows you want, right? So all the 1,000 rows you want. So we just need to type the colon here. Then we separate it by a comma and we give the column, like how many columns we want. Okay, so again, visiting our data set, as we already talked about, we don't require these three columns, like the row number, customer ID, and surname, because it has nothing to do with our exited, right? It has nothing to do with our expected value or the actual output. It has nothing to do with it. So we'll just ignore this. So as we all know, for an array, the indexing starts from 0. So this is the 0th column, this is the first column, this is the second column. So we need to we need to skip these the index till 2, and we need to start at index 3. So from 3 we need all the columns, but again we need this is our training set, and this is our the output, like the y value. So this only column we require in y, but all these columns we require in x. So okay, so just remember, we need column from third index till second last index. Okay, we'll try to keep it as normal, as generalized as possible. So what I need to mention here is 3 colon minus 1. What does this mean? We start from third, the third column, and we go up till minus 1, like the minus 1 is the second last column. We go up to that. So these all should go in our x variable. Now let's see y variable. Again, all the rows we want, so a colon, comma, and we just want the last row in our x. This is the actual output, so we just want the last column. So we just need to mention minus 1 here. That's it. So we are done here. And okay, let's just try to see what all we have included here. Let me just add a code cell here, another code cell, like we just print what we have inputted in x and y. So print x here, print y. Okay, good to go. I guess everyone here. Okay, I mistakenly added here. Let's just delete this cell. Yeah, let's just run. We have just run this part, this code cell. We haven't yet run this code cell. Let's just run it and see if there's an error. No, there's no error in syntax. Now let's just print what x contains. Okay, so here is the thing: 619 France female tel dot 10 something. Okay, so this is the thing: 619 France female 42 dot till estimated salary. We have inputted this thing. We have not inputted the exited in that column. Yes, we are good. Okay, then let's just print y. Yes, it just contains 1010 something. Why? Because this is only the last column. So the last column has only 1010 something. So it just contains that. Good to go. So we have done here. We have imported we have imported the data set. We have put it into an array, and let's just now revisit our data set. Okay. So here we are able to see two columns which are not in numerical value. So geography and gender. So these two columns are not in the numeric values. So we need to transform them to some numbers, right? So the gender, there is only two categories, the female and male. So what we need to do here is like put 1 for the female, put 0 for the male, or vice versa. Just two numbers we require here. But here for the geography column, there is let's just check. We have France, we have Spain, and we have Germany. Okay, so we have 3 different countries. So we need to give some numbers to it. Now now the next question: what numbers we should give to the geography column? We gave 0 and 1 for the gender column. Now for the geography column, what numbers we should give? The first option is like just give France number 1, Spain number 2, and Germany number 3. Example, or vice versa, or something like that. Give 1, 2, 3, the sequential numbers to these entities. But the problem in here is we are including this geography column in our artificial neural network. So what our artificial neural network will think is that whatever the order we are giving to it, like the France we are suppose quoting it to 1, Spain we are quoting it to 2, and Germany are quoting it to 3. So it will think that the Germany is like less related, or it's less important than France. But this is not the case, right? It's not like France. If the customer is from France, there is a higher probability of him living. It's not like that. They are on the same level. So the second option is we just make we replace this geography column by 3 more columns. Okay, so what these three more columns will have? The first column will have France, the second column will have Spain, and third column will have Germany. If in this cell, if it's France, the France column will have a 1, and rest other columns will have 0. If it will have Spain, then Spain column will have a 1, and rest other 2 columns will have a 0. Okay, so we need to do this encoding, like this encoding for the categorical data for these 2 columns. That's our next part, encoding the categorical data. Okay, the first part is the gender column. Let's just the label encoding the gender column. Why? Because we just require two integer values, right? 0 and 1. So we just require 2. So label encoding is enough for us. Okay, so let me again check if anything is like. Should I continue further? Any further thing, ma'am? Okay, this speed
No,
is
continue.
okay. So we are here.
Continue. You are on
Yes,
the
ma'am.
perfect speed now.
Okay, ma'am.
Yes.
Okay, the label encoding the gender column. Okay, so for this we require the scikit-learn library, our favorite library, from sklearn Reprocessing. Okay, the Google Colab. The thing I liked about Google Collaborator is it gives you the recommendation what we are trying to type. So I'll just press enter. So scikit-learn.preprocessing. Yes, so that's the thing. And from this model we import label encoder. Again, we got a thing. Let's just press enter. Let's just give a variable name LE to it. LE is equals to, we need to we need a constructor of it. So label encoder, again, the parenthesis, we have done a constructor here. And now we have our ready. We have our label encoder ready. Now the next step is to fit transform the whatever we have got. We just fit it to our data set, and we need to transform the values. Okay, so first of all, so let's just take our object le dot fit transform method. Fit transform method, and here we need to pass something. Okay, so sorry, here a parenthesis, and in the parenthesis we need to pass something. Okay, this will return something. So this will return the column. This will return the label encoded column. So again, we need to store that column. We need to replace that column, right? Because we don't want this gender column. We need a replacement for it, and which will have 1 0 1 0 1 0 values. So we'll replace it. So let's check what's the index for it. 0 1 2 3 4 5. The index for it. The index for it is sorry, we haven't taken these three columns. So in our case the index starts from here. So credit score is given 0 index, so 0 1 and 2. So our gender column will have a 2 index. So our data is in x, so x is equals to, so now here we want all the rows again, comma, we just need the second column, so 2. And we need to apply this fit transform method to our, again, the parameter we need to pass here is what column we need to apply it on. So again, colon comma 2. So we need to apply it on gender column and here. Okay, let's just print out thing what it has got us. So print x, all the rows, comma 2. We just need to print the gender column. Let's check if it has. Okay, let's just print all the thing. So okay, so let's just run here. Hope it doesn't give us any error. Yeah, let's just run the print. Okay, so now we can see the 619 France 0. Okay, so again we will revisit 619 France 0. Okay, so for female it has given a 0, like encoded it for female it has encoded to 0, and for male it must have encoded to 1. So again, we have successfully encoded our column, or the gender column. Now we need to encode the same thing for the geography column. Now for this thing, as I mentioned you, we will not give 1 2 3 in the sequence, or for the geography column we'll give it in 0 1 1 or 1 0 0. It will, for this thing, for 0 1 1 or 1 0 0, for this thing we require the one hot encoding. It's called as one hot encoding. Okay, so again from sklearn dot compose import column transformer. Yes, it has given us. So we need to transform the column. So simple, column transformer, import column transformer, again from sklearn dot preprocessing module. Again we are using it. Import one hot encoder. Yes, it has given us the recommendation, one hot encoder. Okay, so again we need to build a constructor for it. So let's just take a CT variable, column transformer, parenthesis. Okay, so now what arguments we need to pass here? The first and foremost argument is transformers. This is the first argument, and let's just see what is the second argument. Second argument is remainder equals to. Okay, so what values do we need to pass in these two arguments? For the first, transformers, this tells us like on what column we need to apply this column transformer or the one hot encoding. So here the standard format, which we need to enclose this in square brackets. Again we need to take a parenthesis, then we need to give encoder, like we need to encode it, like we have encoding, we have decoding. What we need to do, we need to do encoding. So encoder is the name for it, encoder. So comma, what technique we need to apply? One hot encoder technique we need to apply, again a parenthesis because it's again a function. And then what column, or yes, what column index we need to apply it for. So let's just check the geography column, right? So this is our 0th column, this is our first column. So geography is the index 1. So geography column has an index 1. So here index 1. Okay, so we are done here, and now let's just see what this remainder is. Okay, so now what we are doing here is we are applying one hot encoder, and we are applying one hot encoder to the first column. Now we need to make sure that the rest other columns remain same as it is, right? We need not touch other columns. So this is the remainder, the parameter here in the to pass pass through. Yes, pass through. So this will make sure that rest of the columns are maintained as it is, and we just need we just one hot encode the our geography column. Yes. So now we have done the fit transform method. Now just apply it to our the array. So x is equals to np dot ct dot fit transform method. Again, we need to fit transform it. Again, a pair of parentheses, and what we need to fit transform is x, and we need to store it again in x. So we have given here x. Okay. So let's just add a code cell again and check what we have done. Okay. So print x. Let's just run it. Hope we don't get any error. Yes, we are good to go. Let's just print x. Okay, so we are now able to see here 1 0 like 1.0 0.0 and 0.0. So what this one hot encoder does is it encodes whatever the column index we have mentioned here. It just encodes it, and it places all the, like, if we are requiring 3 columns, then 3 columns. If we are requiring 4, then 4. Whatever the number of columns we are requiring, it places all these columns at the start of our data set. So now our index 0 column is this, like 1 1 0 0 0 0 0.0 1.0. This is our like first column. So yes, we have successfully encoded France and Germany and Spain here through label encoding. The next step is to splitting the data set into training set and test set. So let's just do it again from sklearn dot model selection. Yes, it has given us a recommendation again. So import standard scalar. Standard scalar. Okay, I have not made a spelling mistake here. Yes, I have not made it. Okay, so we need to again a constructor. Sc is equals to standard. No, it has not given us standard scalar. Yes, standard scalar and a pair of parentheses. Constructor we built. No arguments required for this part. We need a new new array, x train and x test. Okay, so what we need to fill here, as we are splitting the data set into training set and test set, this is our now training set and this is our test set.
Yeah, Prana, so we can wait, we can take a pause for a few seconds and let people
okay,
type this part, whatever you have typed, okay? Because they have to parallelly look into your screen and even code. So wait for a few seconds and then start again.
Okay, I'm just sorry here. I've made a mistake here. Import standard scalar. Before standard scalar, we need to import train test split. Yeah, I'll give you a few seconds to come to this stage. Okay, so we have imported train test split here. Then we require 4 arrays for the training set and test set for x, and the training set and test set for y. So total 4. We require like 4 arrays. So we'll name it as x train, comma x test, comma y train, comma y test. Okay, so these are our 4 arrays, new arrays. Again, we need to call train test split. We need to give a parenthesis. It's a function, and we need to pass the arguments, like on what what are our trainings, what is our main set? Main set we need to transform into training and test set. So our main set, the name of our main set was x comma y. Our main set was x and y. So these two are the first arguments. Then what is the size? What is the size required by us for the test and train size? So any one size we've mentioned, the rest of the size goes for the if we are giving the test size, the rest size goes to the training set, and if we are giving a training size, the rest goes to the test set. So we are giving test size. Test size is equals to 0.2. Like it's a standard procedure. 80% in the training set and the 20% of a data set in the test set. So 0.2 is the feature for the 20%. 20% of our data set in a test set. So then we have again a parameter random state. Random state equals to 0. Okay. So what does this stand for? Random state. Random state is like we want to give the test and the training set. We need to split it in a random fashion. So the random state, like we don't want any partiality with our model, like and so we are randomly giving, like if the first row is given for the test set, maybe the second row may be given to the training set or something like that. So randomly, and the zero mentioned here is it will keep like once it has splitted our data set into training set and test set, it will keep those things as it is. Like it will again not randomly when we again revisit it or something like that for debugging or something, it will not again randomly initialize some suppose
Excuse me, Pranav.
Yeah.
Would you just show the above cell again? One of the participants has a doubt.
Okay.
Yeah.
Okay.
Yeah.
Is this cell
Thanks.
scikit-learn column
Yes,
transform?
yes. Thank you.
Okay. Okay. Should I wait here? Are some of you typing? Okay, I think I should zoom it a bit again. So it be I'll just delete this cell so that I can manage my screen width. Okay, so this is the use of the random state. Now once we have done this, we have splitted our data set into training and test set. We can again check by printing it, but I think the time won't give us, like time is running out of time, so we'll not just which will not just print each and everything. We'll just now see. Okay, so this is ran well, no errors. Okay, I'll keep here. I'll add a code cell here. Just again, max zoom it a bit. Okay, now feature scaling. What is feature scaling? Okay, this is the must step for any artificial neural network. We need to scale everything regardless of one hot encoder or etc. etc. So what is the scaling we require? So as you all can see, the credit score is in some like 800s or 600, something like that, but balance is in thousands. Again, the number of products is in 1, 2 or something, 0 and 1. Again, the estimated salary is some thousands or lakhs. So we need all on the same platform, right? So that's why we require a feature scaling. So again, from sklearn dot now pre-processing, we import the standard scaler. Yes. Again, we create an object. SC is equals to standard scaler. Pass a parenthesis to it. Yes. Now okay. So if you're typing still this, okay. We have taken the object for the standard scaler. Now we need to pass the standard scaler for a training set and test it, right? So x test, something we need to do for the x test and something we need to do for x train. Okay, so our y test and y train are already in like zeros and ones. So we need not do anything. We need not touch anything to it. Okay, so let's just first come to train. Okay, I first need to mention here train and here test. I'll tell you why. Okay, so first sc dot fit transform method. Fit transform method for fitting and transforming our data set. So x train we need to pass here. So now, okay, so why I did that, like why we require x test down and x test up. Okay, so here we'll write sc dot only transform, will not fit it again, because what it does is we require the same scalar, right? Whatever the scaling is done for the x train and x test method, we need the same we need the same scalar basically to transform both the cells. It shouldn't happen like for training we have done some, we have taken suppose xyz scalar, and for test set it has abc scalar. We'll lose information in that. So just to avoid the information leakage, we just transform the test set and we fit the method in the training set. Okay, so as an argument again test, we need to pass the test set here. Okay, so we are done here. Let's just run it. Good to go. So yes, congratulations, we have just completed the part 1 of our building ANN. Like just we have done the data pre-processing. We need not do the data pre-processing anymore. Okay, one more thing I need your attention here is you can just check, we have no NaN, or we have no value cell. We don't have any cell of this thing. Either we have a 0 for that cell or something, some values we have. If this whole data set doesn't contain the NaN feature, like the empty cells basically. So if that is present, you again need to do something for it. Like it's an again different story. We did not go into that. But if some cells are empty, you need to do something else for it. Okay, so yeah, we ran this. I guess yes, we ran this. Now let's enter the part 2, like the building the ANN, actual building the ANN, and then we'll go in the part 3, training the ANN. Now initializing the ANN. Okay, we need to initialize our ANN with all the layers and all the sequence of layers, as we all spoke, like input layer, output layer, hidden layers. We will do it here. Okay, so yeah, so let's just create another variable ANN, and now we require our most important library, TensorFlow. So remember, we have given it a short form TF. So TF dot keras, we need a keras library from it and models from it. Okay, again from models we require a sequential, because we want a sequential sequence of layers, right? We want some sequence of layers. So this sequential method, this sequential function is used to create the sequence of layers. Okay, so we are done here initializing the ANN. Let's just run it. Yeah, we are good to go. Now adding the input layer and the first hidden layer. Again, I need to add a code cell here. Okay, so for the first thing, we need to add the input layer and the first hidden layer. Input layer is only one. Hidden layer might be like any numbers hidden layer. So here we have 2 hidden layers. So the first we'll add the input layer. Okay, so the input layer and the first hidden layer, obviously. So ANN again, ANN dot add. This is the simple method, ANN dot add. Add method. If you want to add any of the layer, just require this method, ANN dot add. Okay. What all we need to pass here? Again, TensorFlow. We require TensorFlow dot keras. TensorFlow dot keras. Here we require layers because we require layers. From this we require the dense thing, like the dense thing. It's a standard thing. And again, for this function we need to pass some arguments. Okay, another thing I forgot to mention here is the Google Collaboratory gives you a nice recommendation on what all parameters you need to do, what all parameters you require here. those who are doing the implementation on their own Jupyter notebook, like the localhost Jupyter notebook, you won't get this like this recommendation, like what all arguments you need to pass. So the first argument, let's see, units. Okay, that's a compulsory argument, and the activation, it's not the compulsory, but we'll pass it. The activation function. We'll not worry about the rest of the features. Okay, so let's just dive back. Okay, so here in the first argument was units. Okay, it has given its recommendation. The second parameter was the activation. Activation is equals to, okay. So now units. The number of units I'm giving here 6. It's basically the 6 is not a random number. It's the like units is basically the number of neurons, like the number of circles we saw, right? If you all can remember the number of circles in each layer. So that the number of circles is this number of units. So this is a 6. This is number. It's actually trial and error number. For 6, we get like maximum accuracy. We'll see what accuracy we get. But for 6, we get some decent accuracy. You can try it with 5, 4, any number. Like, don't just go for 100 or something, but type a reasonable number, and you can just play with that number and check what accuracy you get. Okay, so number of units activation, number of units is 6. We have got it, and the activation function. We saw in the theory, like we require an activation function for our hidden layer. So okay, so what activation function we saw? We saw sigmoid activation function, and we saw a rectifier activation function. So I told you that for the sigmoid activation function is mostly used in the output layer. Why? Because we are predicting the probability, so it's most useful in the output layer. Whereas the rectifier function is mostly used in the hidden layers. And so here we are going to use a rectifier activation function, and the code name, as we already discussed, is ReLU, R-E-L-U. So you need to just type it ReLU, and yes, we are done. Let's just run it. Okay, we have successfully created an input layer and the first hidden layer. We are just building it the structure. We haven't yet passed our arguments, right? We are just building the structure of the neural network. Okay, now adding the second hidden layer. The process is same for adding adding any layer, unless and until you need to change the activation and the number of units. So I'm just going to copy paste the above thing here, and the same thing will add the second hidden layer to our model. So no, I do not need to change the 6 and the activation function ReLU here. So again, we are good to go. We just run it. Yeah, we are good to go. Now adding the output layer. Okay, actually the same thing I'll again copy paste here, but now in the output layer, as our output is binary, right? Like our output is like just exited or not. So 1 or 0. So it's a binary output. So we require one unit there. So that's the number. So the number of units here is just 1. If you have a categorical data, like something, if you have some car, aeroplane, or motorcycle, or something, like the types of vehicles you need to predict, so you have a categorical data. So at that time, you need more number of units, because each unit will depict your each category. So yes, the activation function, as we already talked, for the output we require sigmoid. So simply sigmoid is the name. There's no short form for it. Okay, so we are good. Let's just run it. Yeah, nothing to worry. Okay, so we have successfully completed with part 2. I'll just wait a few 2-3 seconds for it. If you have like just missed out anything from here and from the part 2, you can just cope up with us. Okay, I think we should go ahead. Now let's just enter the third part. That is the training our model, like training the ANN. Now in the part 2, what we did is just build a structure of ANN. We initialize the ANN, We build the input layer and the hidden layer, the second hidden layer, and the output layer. We just build the structure of it, the rough structure of it. Now we need to pass everything to it. So like training everything. So the first thing is compiling, obviously, and simple as the name suggests. We require the compile method here. So ann dot compile, it gives us a recommendation. Compile. Okay, so now what arguments we are having here? Let's just check. Optimizer, loss, and matrix. These three we are going to focus on. We are ignoring the rest of the things. We are setting it to default. Okay, so the first is optimizer. The second is the loss, and the third is matrix. Okay, so optimizer. So now what is optimizer? Optimizer is we got the error function, the cost function. If you all remember the theory, we got the cost function there. So we need to minimize that cost function, right? So for the minimization, we saw gradient descent technique. So if we want we want to apply that gradient descent here. So that's the optimizer basically. So it has a name Adam. So this is basically for gradient descent. So it's for basically stochastic gradient descent, but you can it's and Adam is best algorithm to do the stochastic gradient descent. But imagine we have just saw gradient descent, so imagine it's gradient descent there, gradient descent happening in that Adam thing. Okay, in the loss parameter, we require binary cross entropy. Binary cross entropy. Yeah, haven't made any spelling mistake here. Yeah. Okay, so what is this binary cross entropy? Okay, so our it's our binary classification, right? We just 0 and 1 exited or not. So we give here a binary cross entropy. If it's a multi-class classification problem, you give a categorical cross entropy, categorical underscore cross entropy as an argument here. Okay, then matrix. We want to predict the accuracy, right? So we'll just pass accuracy. We want to calculate in a matrix format, so accuracy. Yes, that's it, and we'll run here. Hope if you haven't made any mistake. No, you haven't. Okay, so training. Now we have just compiled it. Now the training, the NN on the training set. The training set, as you all can remember, is x underscore train. It's an array. So NumPy array. So we are going to train our neural network on that training set. So again, ann dot fit method. Ann dot fit method, like x an argument. Okay, let's just skip it. We'll pass the arguments x train, comma y train, x train and y train, comma. We need two more arguments. Batch size. I'll walk you through it. What this is, and the second is epochs. Okay, so batch size. We saw in the last step, in the last PPT, that okay, so here is the PPT. In this step, the batch learning and reinforcement learning. So for the batch learning, this is the batch size we are implementing batch learning. So the batch size is again, you can be like this is required for artificial neural networks, and it can can be like 35, 10, something like that, but I am giving here 32. You can play with this number, and you can just do it. And for the safer side, epochs, I'll give it 100. So 100 times all this procedure is gonna repeat. Okay, so we are done here. Now we require some space here because it will start running, and let's just run here. Okay, so you can see here it started to train our model. So epoch 1 on 100, epoch 2 on 100, epoch 11, 12, 27, 28. It's quite fast. So yeah, we have to reach 100 epochs. We have given a parameter 100, and you can see here the accuracy. The accuracy is slowly like 86, 85, 86. You got 75 here somewhere. If you have mentioned here, if you have noticed here, 73. So that's the need. That's basically the need for that epochs. Like if we did just one epoch, and at the first epoch only we got, suppose, accuracy, let me just find where we got 76 or something. I just saw somewhere. Okay, leave it. We somewhere got 76% accuracy or 0.76, something like that. If we did just one epoch, we would like feel, oh, where we went wrong. Our accuracy is so less. But so we need to like redo all these things. And yes, all changes saved. It is auto saving everything. So at the 100th epoch, it got the 86 accuracy. Okay. Now we have trained our training set. Now we haven't checked the accuracy on the test set yet. Okay. Let's just do it. We have just got the accuracy on the training set and we have trained it. Okay. I guess. Okay, so this is the epoch. This is the these are the accuracy differences: 0.86, 0.8645, 0.8648. These are the small differences you get here. Mm, okay, let's just go to the first. Okay, here you're able to see, yes, the accuracy is 77, like 0.7788. So here our accuracy was 78%. Again, it increased to 79, 79, 80, and finally at some, like it gradually increases. Look, 81, 81, 82, 83, 83. Okay, and at around, okay, let's just see. Okay, at around somewhere in the 56th epoch, we got an accuracy of 86%. So and obviously the loss also keeps on decreasing. Here the loss was 0.4 and here the loss is like 0.39 or something like that. So this is very important. You need a lot of epochs. Like you just can't do it one time or like 2-3 times, because here only you can see the difference. In the 56th or something around in the epoch, we got accuracy like 86%. So yes, you need to do the epochs. So let's just, okay, so yes, we have completed yes, we have completed the third part. And select it so, like, you need to select it so that it won't be less, like it should also, it should not also overfit our model. I guess overfitting and underfitting concept might be over. If it's not, leave it. It's something we actually don't have time for it, and otherwise I would have explained it. Okay, so predicting the test set results. Now we are entering the fourth. Okay, I made a mistake. Okay, we are entering the fourth phase. Like, we have trained our model, we have done everything on our training set. Now let's just do it on our test set. Test set is something which is not given to us. Like, it's completely hidden. We are all working on the training set. Test set is just kept for us for the testing of our model, and we have not yet. We are not knowing what the test set is, and so let's just predict the result on the test set. So again, we require some like whatever we are predicting, like we are the y cap and the y actual. So here for the training, we didn't require the y cap, like we require the y cap, but for the for predicting the tested results, we require that y cap. So let's just rename it as y pred, let y predicted y, and arn dot predict method. Simple. Predict method. Okay, predict method on what we need to predict? The x test. The x test is the array we need to predict our y pred on. Okay, so the second thing. Now it will predict something. It will predict something in 0 and 1, right? In 0 and 1, but we require it as a probability. Like the bank requires us to give them the probability, like the 86% chance that this customer will leave the bank, or 92% chance that this customer will leave the bank, or something like that. So sorry, it is the probability. Here we need to give them the actual, like 0 or 1. They want just a category like don't tell me the what is the percentage of it. Just tell me, would he leave the bank or not? That's a simple thing mentioned by the bank. So for this, we need to, like we are getting the probability, so we need that probability again in some zeros and ones. So again, ypred, we need to store it again in ypred. So ypred is equals to Now in bracket, what we need to do, it's a simple thing greater than 0.5. Okay, so what it will do, if the if in this column ypred is like greater than 0.5, if the probability is greater than 0.5, we'll simply put it, will simply return 1, and so 1 will be stored at that row. If the probability is less than 0.4, that means it's 0, that the customer won't leave the bank, and thus the probability like 0, so we are storing it in the ypred. Okay, so and then let's just print our ypred, that's our y cap and y side by side, so that we can easily compare what all things our model did. Okay, so first we are printing, so print method, print, then numpy. Okay, so I'll explain this, I'll just type everything. Concatenate, we need to concatenate both the things, it's just a function again. Then y, okay, y is small, ypred dot reshape, then again we need to parenthesis len ypred. Don't worry, I'll give you some time to let just do everything. Let's just first type everything. Okay, comma ytest dot reshape. Okay, reshape, again parenthesis, again the same function, same thing, length of ytest. Okay, ytest comma 1, after two things comma 1. Oh, I made a mistake somewhere. P dot concatenate. Excuse me. Okay, so yeah, we did a mistake somewhere in the number of brackets. I guess, let's see. Wait a second. So this is our first bracket. First bracket should end here. Second bracket opening, third bracket opening. Yeah, here we made a mistake. Okay. So, okay, reshape len ytest comma 1. Okay, I think we have not missed something. Let's just run and check. Okay, we have done something wrong here. Okay, the brackets have to check. Just give me a second. Okay, again we did here something. Extra bracket. Okay, I guess we are good to go. Yeah. Okay, so take a few minutes and just type it. I'll explain till the time what it indicates. Okay, so what we are trying to do here is this is our ypred, is our y cap, and this is the y test, which is the actual output given to it. We are trying to print it side by side. So for printing it side by side, we all noticed above, like it is horizontally, like, so we want it like vertically to for the good comparison. So just reshape it from the dimension, what the dimension would be, the length of ypred comma 1, and similarly the dimension of y test will be length of y test comma 1, because we want a single column, so comma 1, and the whole thing in a in a single column. So this whole thing, that the whole thing, you can see the brackets, square brackets here. So this whole thing, one square bracket, so it's a one column. So here it's the one parameter here, and so we concatenate both these things, so we could see both the things with side by side, and we print it. So here we can see the y pred, that is what we predicted was 0 and the actual was 0. Yes, our ANN model got right here, 1 1, it got right here, 0 0, it almost went correct everywhere. Okay, now let's just make the confusion matrix to test what the accuracy we got and how accurate was our model. Okay, so from sklearn, again sklearn dot matrix, we need to import confusion matrix, and we need to input accuracy score. So accuracy, accuracy score. Okay, so what we want to import is confusion matrix and accuracy score. So for confusion matrix, let's take CM as the variable. CM is confusion matrix, and let's pass some arguments to it. Okay, so what are the arguments? Obviously, y test and y pred. Y test comma y predictions, because whatever we predicted and what was the actual, we need a confusion matrix for that. Okay, so what is a confusion matrix exactly? I will just explain you now. When we run this cell, we need to print this confusion matrix. So print CM, and we need an accuracy score, ACCU, accuracy score. Okay, accuracy score, okay, it's a function, accuracy score for y test, again y prediction. Okay, so let's just run here. Oh, cool. So the first thing here you are seeing is the confusion matrix, and the second thing you are seeing is the accuracy. So we got an accuracy of 85%. So whatever we did, like the units we took 6, the epochs we took 100. You can play with these factors. We applied the ReLU function for the hidden layer, applied a sigmoid function for the output layer. You can change these and just check what the accuracy you get here. This is the final accuracy of our model, and this is the confusion matrix. Now what is the confusion matrix? Okay, so here you're all able to see the 4 values. So what is this? 1505. So this 1505 is the true positives, or let's just try to understand what is the true positive. So whatever like we are passing 2 arguments, right? Y test and y pred. So whatever the actual output was, we predicted the same output. If that's the case, it's included in this true positive part. So it's 1505. Then it's the true negatives. True negatives is 211. What is the true negatives then? Okay, so the actual value was negative only, and we also predicted it as a negative. I mean negative as in the sense like in 1 and zeros. Don't misunderstand me. Okay, so the output was the customer was leaving, and we also predicted it as a leaving. So it's a negative thing for us. So yes, we predicted it true. So the false it's a negative. So 211, that's value here. Then this 90 and 194 are the 2 values where we get the we call it type 1 error and type 2 error. You'll study what these are exactly, but let's just tell me what these are. Like our y test, like the actual value was 1, but we predicted 0, or the case the actual value was 0, or we predicted but we predicted it 1. So it's not correct, right? The actual value was 1, but we predicted it as 0, so it's not correct. So these 2 things are telling us that. So 90 and 194 are telling us that 2 values. So yes, congratulations, you have successfully built an artificial neural network and trained it, and for a 1,000 rows data set. It's a good thing. You can pat on your back. Yes, and that's all for it. That's all for the session.